Anybody who knows me knows that I always make the same joke, that the only person that calls me Patrick is my mother when I'm in trouble. So I don't respond to that name. If you want to get my attention during the talk, shout out Paddy. It's with D's, not T's, for the Americans in the room. And that's the best way to get my attention. Okay, so I'm supposed to talk to you about WIMPs and SUSY. Okay, and there's considerable overlap in what I'm going to talk about with some of the other lecturers. So it's probably worth me just pointing out there will be, I'm in some sense the warm-up act for some other people who are lecturing. So you've already seen Jim's talking about early universe stuff, and he's going to talk about freeze-out, which is something that's going to be important for the WIMP story. So you'll hear that multiple times in multiple different ways. In addition to that, Tong-Yang Lin is going to talk about other dark matter models, non-WIMP models. As we go on, you'll learn what I mean by WIMPs in particular. And she's also going to talk about direct detection. But I'm also going to talk about direct detection. So again, I'm sort of the overview, superficial. I'll get all the minus signs and the factors of 2 wrong, and they'll come along later and correct all my mistakes. At least that's what I'm hoping. Dan Hooper is going to be talking about indirect detection. So there's overlap with that. Less overlap, but still important, is Mark Vogelsberger is going to talk about n-body simulations. And finally, Anson Hook is going to talk about axions, which are can be a dark matter candidate, a non-WIMP dark matter candidate. So there's considerable overlap with all these people. We've discussed a little to try to make it not complete overlap, but it doesn't hurt to hear things twice. Okay, so actually let's do a quick poll. How many of you have written a paper on supersymmetry? Written a paper, done some research on supersymmetry. Okay. Some of you. If I'd asked this question 10 years ago, I would have thought every hand would go up, but such is the times. But nonetheless, I'm going to tell you all about how awesome supersymmetry is. But before I do that, maybe I'll give you the overview about dark matter in general and WIMPs in particular. How many of you have written papers in dark matter? Ah, that's what I expected. Okay. All right, so some of you will know this story, but it's Monday. You've got 4 long weeks ahead of you, so let's start with something you know to make it easy. So I'm going to attempt to explain this famous pie chart, right? I'm never going to get the angles right. But 73% of this is the matter-energy budget of the universe. Okay, this is if you go out and add everything up and weigh everything and ask how much stuff is out there, you get this famous pie chart. This chart. 23% is dark matter, and then this is the standard model, an embarrassing 4%. And in fact, if we're totally honest, only 1/10 of this 4% is interesting, right? In the sense that it makes stars and planets and good stuff like that, and the other 3.6% is intergalactic gas, which to me is not that interesting, but that's just my tastes. Okay, so this is the story, what we have, and I'll try to explain what it is. Am I talking loud enough? Is my handwriting legible? Good. Okay. So dark matter is almost definitely beyond the standard model physics. Supersymmetry may or may not be beyond the standard model physics in the sense that it may or may not be out there. But I'll try to talk about both and connect the two. So let's go through why. I'm not going to talk about this stuff at all. Too hard for me. So let's try to focus on this and try to understand why we're so confident there's 23% of dark matter out there. So this will be the potted history in no particular order. So you can go back and you can, to the 1930s, you all know who Fritz Zwicky is? Right? So he went out and he looked at the movement of stars in the Coma cluster, right? And he found that using the virial theorem, he could work out by looking at the motion of the stars, looking at the average speeds, the average kinetic energy. He could relate that using the virial theorem to the potential that they were moving in. And then he could add up the number of stars in there and work out all the visible stuff contributing to this gravitational potential. And he found that there was a huge discrepancy between this side and the observable part of this side. And in fact, he claimed that as much as 90% of the coma cluster was what he called, why my German isn't very good, Dunkel material or dark matter. So that was back in the 1930s or so. And this has been repeated many, many times since then in many different systems. Another way it's been done in a very sort of analogous way is Vera Rubin. So that was Zwicky. So Vera Rubin, am I going to spell it right? Yep. She did the same thing, but at the galactic scale. So rather than a cluster scale, she looked at the motion of stars inside individual galaxies, and then she plotted these as a function of the radius from the center of the galaxy, the speed of the stars, and she found the following sort of relationship, where this turnover is probably at tens of kiloparsecs or so, right? And she can do exactly the same thing of totaling up the number of stars that you see on an orbit interior to one of these outlying stars. So these, the typical size of a galaxy like our own in terms of the stars is that you have a disk. Let's go over here. You have a disk with a bulge in the middle where there's lots of extra stars, and that we live about 8.5 kiloparsecs out from the center, and the overall length of these arms coming out is maybe 10 kiloparsecs, 15 kiloparsecs, something like that. Okay? And so she was looking at stars way, way out on the exterior of these galaxies, working out how fast they're moving, and then adding up the number of stars that were interior and working out whether they could get in those orbits. And so it's just a simple thing, right? The velocity, you ask what's holding them in their circular orbit, and it's a simple undergrad problem. And you would expect, because basically all the stars are in the middle, that as you get further and further out, that this mass essentially asymptotes to a constant. You've got no extra material growing as you go out at these far edges. And so then you would expect this velocity, if this is a constant, you expect this velocity to go as 1 over r, right? Which means that it should look like this, at least to the large r limit of it, should look like that, and it doesn't. And so the fact that you see this plateau tells you can work out what the radial dependence of this mass is. And you find that the total mass, or Vera found that the total mass has to go like r, and so that tells you that the total mass scales as the density as a function of r times r squared. So then this tells you that the distribution, there is some matter that is not in stars, because she didn't see it, that only drops off as 1 over r. It doesn't asymptote to a constant at the large r limit, right? And again, this is telling you that there's some extra material holding these stars in orbit that you can't see, and so that's another evidence for dark matter. Now you can do approximately the same thing, but locally, right? You can ask, how are the stars moving around where we are? And from their motion, infer what the local potential is. And again, subtract what you see from what you don't see, and work out how much dark matter there must be local to us to get the stars local to us to move in the way they move. And you find that, again, there's evidence for extra stuff, and that the local abundance of dark matter is this famous number. We'll come back to it many times. But let me just write it down once. Actually, let me not worry about the error bars, since it all depends who you ask. Okay, so this is telling us in our vicinity, there is about a third to 0.3 to 0.4 GeV per centimeter cubed of dark matter stuff at a position 8.5 kiloparsecs out from the center of our galaxy. And a good place to go to hear the story of this, like Jim said, is the PDG has a very nice up-to-date explanation of how we arrive at this number with all the error bars that are associated with it. Okay, so that's the first piece of evidence for dark matter. But there's more. Any questions? Or you all know this stuff? Okay, so Jim already mentioned the next observable just at the end of his lectures, which is the CMB, right? Looking back and looking at the surface of last scattering and looking at the fluctuations across the sky. It's homogeneous to very high precision, but there are some small fluctuations. And the measurement of these small fluctuations has got more and more precise in the last couple of decades, starting with Kobe and going all the way to the present day with Planck. And those are full sky surveys, and then there are more precise fractions of the sky survey, like the South Pole Telescope and things like that. And you can look at the fluctuations in the temperature as a function of angle, right? And because you're looking at the sphere, the surface of last scattering, the sensible way to look at these is in terms of YLMs. Right? And you can look then, so that you see these fluctuations on the sky, and you can look at the temperature power spectrum. So you can look at the spatially averaged fluctuations in T squared, and you get this beautiful picture that I cannot do justice to with my artistic abilities. So you get the L plus 1, CL over 2 pi. And Jim already explained what these CLs are, right? You expand, and then they are the average of the ALM squared, or the mod of ALM. You just do this, and you get this beautiful picture that looks like that, right? And the exact location of these peaks tells you something. The first peak tells you something about the geometry of the universe, whether it's flat or negatively or positively curved. It tells us that the universe is flat. And then these next couple of peaks tell us something about the abundance of various types of matter. Matter that's coupled to photons and matter that isn't coupled to photons. And then these subsequent wiggles also tell us about these things. You could think of them as cross-checks, right? Consistency checks of the parameters that you're extracting from these first few wiggles. So again, the location and height of these wiggles are essentially determined by about 10 or so parameters, and one of those parameters is the amount of dark matter, and the number that you get out is non-zero. And again, you wouldn't, if you tried to build a universe without dark matter, you would not get a CMB spectrum that looks like this. And one of the reasons you wouldn't is because these wiggles are the formation of structure. Right? And structure, as Jim said, can only start to form once you've crossed the period between matter and radiation equality. So once we go from a radiation-dominated universe to a matter-dominated universe, then structure can start to grow. It grows very slowly in radiation-dominated universes. And so how much structure you get, how big these wiggles are, will be determined by when that transition happened. And the more matter you have, of course, the earlier that transition would have happened. But the baryon part of matter is still, even though you've gone from radiation dominated to matter dominated, the baryons are still coupled to the photons. They sit in equilibrium. There's this baryon photon bath. And so any overdensities they have get washed out because they're coupled to the photons. But dark matter, if it's out there, isn't coupled to the photons, and it can seed the formation of structure. So the fact that you get this structure, the shape you get is basically driven by when matter radiation equality occurs and how much of that matter is not coupled to the photons. And again, by fitting these wiggles to the standard lambda CDM model, so that means cosmological constant plus cold dark matter, you can work out the amount of dark matter out there, and it's consistent with the pie chart I showed you earlier. So you can keep doing this exercise. You can look for the same wiggles in different systems, right? In addition to looking for it in the temperature fluctuations of the CMB, you can look for it in the wiggles in the matter power spectrum. So you can look at, let's see, how do I want to say this? So you can look in wavelength space, or if you like, so K, which is 1 over a length scale. You can look at the power at various wavelengths, or various inverse length scales. And you see this very distinctive shape. This is measured on different length scales. It's measured in different ways. So this part of the sky, measuring the matter power spectrum, is measured using CMB observables. Then you can look at how much power there are at different length scales from looking at clusters of galaxies. Then you can look at using weak lensing observables. And down here you can use Lyman alpha. And then down here, oh, well, there are wiggles all over the place. Let me put some small wiggles in. You can look at baryon acoustic oscillations. So the great thing about this diagram is, in fact, these observables, these different ways of measuring this power spectrum slightly overlap, right? The length scales are sensitive to, the CMB is sensitive to this range, and clusters has a small overlap with that range. Weak lensing, again, has a small overlap. Using Lyman alpha observables has a small overlap, and so on and so forth. So you now have this, by gluing together all these different observables of the size of fluctuations on the sky at different length scales, you can map out this whole shape. And again, the shape of this and the wiggles are basically determined by those 10 or so parameters, one of which is the amount of dark matter. And this change in slope, this break here, is again determined by when you have matter radiation equality. And of course, when the energy density in matter is equal to the energy density in radiation will depend critically on how much dark matter there is out there. So the location of that peak is also sensitive to the amount of dark matter. Okay, so these are all different observables that point to the same they're all measuring, to some extent, when this occurred. And I was claiming that the details of this structure formation are also sensitive to how much of the matter is coupled to photons and how much of the matter is not coupled to photons. And I'm going to call the stuff that isn't coupled to photons dark matter, and we'll come back to that in a minute. So, oh, Jim's right here. You're going to talk about BBN at some point, right?
No.
No? Ah, okay. All right. Then I'm going to talk about BBN for 5 minutes rather than 1 minute. So let's talk about BBN. So BBN is very cool. And BBN is another piece of evidence that there is matter out there that is not standard model matter. Okay. And BBN is probably, it's very cool to talk about BBN in Boulder, because, of course, the original paper that explained all this was written by 3 people, Alpha, Beta, and Gamov, who was a Boulder. Not at this time, but later a Boulder, and he has a tower named after him, which we are all going to go drink wine in later. So, so he's a local. Okay, so the story here is you can go back in time to the early universe till about, let's say, a few seconds after the Big Bang, right? Or a few seconds after reheating, let's say. And you'll find that the universe is basically a soup of a few standard model particles, some protons, some neutrons, electrons, and photons, all kicking around and in thermal equilibrium with each other. And of course, the universe is expanding and cooling. And once the temperature crosses about an MeV or so, which happens at times of order 10 seconds, something like that, you find that the processes that keep this system in equilibrium are now too slow, and the sort of forward-backward, this forward-backward reaction stops. Right, the weak interactions, which were keeping the number of protons and neutrons in equilibrium with each other, and in equilibrium with the number of electrons and neutrinos, stops being efficient, and you have, this is the first example we'll see of a process called freeze-out, which will be very important, and we'll go into more detail for dark matter, but this is freeze-out in the standard model, right? The weak interactions have now frozen out. Okay, so what happens? So at that moment, these things are no longer in thermal equilibrium with each other, and they just go along their merry way. And so you can ask, what is the number density of neutrons over protons at this time? Okay, so I'm telling you the temperature is around about an MeV, and we all know that the neutron and the proton are not quite degenerate in mass. So if you were to take a thermal distribution of neutrons and protons at that temperature, you'd have a slightly different number of neutrons and protons because neutrons are slightly heavier. And so you find that the ratio of the number of neutrons to the number of protons is just what you'd expect from a Maxwell-Boltzmann distribution, right? That there's the extra cost of the extra mass of the neutron divided by the temperature. Okay? And if you go to the PDG and remind yourself of what these masses are, look it up, you'll find that you get the number 1/6 or thereabouts. Okay? And at the same time, you can ask, what is the ratio, let's call it eta, the ratio of the number of baryons or the number density of baryons to the number density of photons. Okay? And this is this famous number that you probably all know. It's about 10 to the minus 10. So there's a lot more photons out there than there are baryons. And this number is basically going to be the key to everything in BBN. Okay, the fact that there are so many photons out there will drive the dynamics. And then the other thing you need to know is that if you want to make heavy elements, so you start with protons and neutrons and you start to cool, they're going to glom together and they're going to start building up and making heavy nuclei, right, which are just collections of protons and neutrons. And if you want to get to anything other than a hydrogen, so a bare proton, you have to go through deuterium. So if you go and open up the nuclear data tables and ask, how do you make heavy elements, you'll find that this is the opening reaction. Right, a proton finds a neutron, makes deuterium, and kicks out a photon, and then deuterium can join up with protons and turn into helium-3, or two of them can come together and turn into hydrogen-3, is that right? Oh, plus a proton. Or once you've got one of these, you can join it with deuterium and get helium-4 plus a proton. And this is wrong because I haven't conserved baryon number. And I think that's, did I do that right? Oh, sorry, no, plus a photon. I haven't conserved energy and momentum. Anyway, the list goes on and on and on. But the point is, to get to anything heavier, you have to go through deuterium. And this is the so-called Deuterium Bottleneck. Right? That you have to go through deuterium. And this has implications because deuterium has an enormously small binding energy. So the deuterium binding energy, what am I going to call this? Okay, so it's about 2.2 MeV. And so it's really easy, even if you make it, for deuterium to wander and hit a photon, and for that photon to immediately dissociate deuterium. So if you want to get to one of these subsequent reactions, you have to have that the number of photons around is small enough that deuterium survives. GeV to EV or thereabouts. And that's what I'll call WIMP dark matter, weakly interacting massive particle. Then, but to put it in the context of what other people are going to be talking about, so that's because, as we'll see, this thermal story, if we assume that the interactions dark matter have are to the weak interactions, or weak scale in nature, then this thermal story will only work over this narrower range. If you assume that dark matter has additional couplings, if there's a dark sector with its own gauge interactions, then this thermal story can be made to make sense pretty much from MEV to PEV, and that's something that Tong Yang will talk about. Right, she'll talk about dark sectors and more complicated structures and more complicated interactions that allow this thermal story to go ahead over a wider range. But so the point I'm trying to emphasize here is that the range of possibilities is vast, right? Anson's all the way down there. He may talk about fuzzy dark matter, I'm not sure, but the QCD axions and axion-like particles are way down at that end. They're bosons. And then people interested in the LIGO result are way up at this end. And the WIMPs, which are maybe the oldest example of dark matter, the ones that had the most papers written about it, is a fairly narrow range in the middle. So there's a lot to think about and a lot to work on. So there's plenty of opportunity for clever ideas, which is where you come in. I have 15 more minutes, is that right? Great, perfect. So, yes? How much of this line has been tested? Brilliant. Not much. Not much. So ADMX and experiments like it, I'm not going to have a very narrow range. They've ruled out QCD axion being dark matter over a very, very small range of masses. Okay. There are non-trivial constraints from observables, right? N-effective and large-scale structure and things. But there's another axis I've suppressed, which is going this way, which is all the caveats and the model building and the things you can do to get around all these constraints. So, wow. I would probably say that any of these masses is still in principle allowed. But we don't know anything about dark matter other than it's out there, right? And which is the next point I was trying to make, which is, I'm glad you asked, that all the evidence I've given you so far have been about dark matter's gravitational interactions. Okay? And we haven't, and which candidate it is changing something other than its gravitational interaction. Right? Down here we're saying that it has something to do with the strong CP problem, or at least that it's a pseudo-Goldstone boson of some broken symmetry. And up here we're saying that it has couplings to the weak interactions. And over here we're saying that it's actually made through some weird density fluctuations in the early universe collapsing into black holes. And all those statements have got nothing to do with gravity, right? Or at least the gravitational interactions we've used to probe it so far. So I should point out some historical notes. This is not without precedence, right? That we've discovered new physics only through its gravitational interactions. You all know the story about Neptune, right? Neptune was discovered through the wobbles in Uranus's orbit. And in fact, they were mapped out so perfectly that once the mathematicians had worked out what it meant, they could tell the astronomers to go and look at that particular part of the sky. And once the messages got out, it was basically discovered within about an hour of observing, because they knew almost exactly where Neptune should be, just from its pure gravitational interactions, right? So that was a discovery of real dark matter, a new planet. In this case, it happened to be a macho, so the analogy is not great. But the discovery of Neptune was the first use of gravitational interactions to discover dark matter. Okay, the second use is also not a perfect analogy, but of course it was Mercury, right? The retrograde orbits of Mercury was a gravitational phenomenon that could not be explained by Newtonian gravity, and it needed to use GR to explain why Mercury moved that way. And unfortunately, so this is, if you like, really a macho, because it was baryons that they found. And this one was the discovery of GR, or it wasn't really the discovery of GR. GR was pure thought, but this is one of the confirmations of GR. And unfortunately, this is most like MOND. Because it changes the rules, changes the laws of gravity, just in the same way that MOND does. And I'm not going to talk about MOND at all. But this fact of using gravitational interactions as your way into new physics is not unheard of. Okay. So, okay, good. I have just enough time to tell you why we like focusing on this part, on the WIMP. Okay, so let's... Because it would be really boring if dark matter only had gravitational interactions. But that could be life, since the only way we've seen it so far is through gravity. But there's another more exciting possibility that we'd like to explore that leads us down our interesting rabbit hole. Okay, what is that interesting rabbit hole? So this is freeze out. Freeze out of dark matter now rather than BBM. Okay, so imagine that there was additional interactions of dark matter. In particular, imagine that there were interactions like the following. So dark matter has some interactions with us such that if two dark matter particles hit each other, they can annihilate into standard model. Then this running the reaction the other way tells you that in the early universe where there was a hot bath of standard model particles, you would also automatically populate the dark matter, and this is the thermal story, right? And you can ask what the mathematics is to try to understand this process, but before I do the mathematics, so let's see, how do I want to say this in the remaining 5 minutes? Okay. All right, the right way to understand this is to try to write down the Boltzmann equation in an expanding universe. Okay, and the real thing that's at the root of the Boltzmann equation is the so-called phase space distribution of dark matter, which is basically telling you as a function of momentum and time, and really all it cares about is magnitude of momentum because the universe is spherically symmetric and everything, so I can't pick a direction. This basically tells you, how much dark matter is there. This is the phase space distribution. How much dark matter is there of a particular momentum, or how much of any species is there, and what is this distribution? And this follows a Boltzmann equation, right, in an expanding universe that is the following. And now I can piggyback off what Jim was telling you earlier. You all know what the scale factor is now, right? So this is another way of writing this is just to call this H, the Hubble constant. So this is a complicated equation that I'm not going to solve, but I'm going to write it down. P is momentum. Yeah, so this is the magnitude of some 3 momentum. So this is asking at a particular momentum how much is there of this species at a particular time. And then integrating over, so I think there's probably a G here, counting the number of internal degrees of freedom. Integrating this tells me this. Okay? I think that's right. As a function of time. So this is a function of P and T, and this will be a function of time. So I really care about quantities like this. I don't really care about these Fs, although deep down I might, but for the level of these lectures, I think what we're going to do is we're going to integrate this equation and work entirely in terms of number densities. I don't know what level Jim's going to get into this, whether you're going to try and solve this equation. Okay, you'll talk about Boltzmann equation, okay. But this is basically, so this is just determining the evolution of this phase space distribution as a function of time in the expanding universe. That's the left-hand side. And the right-hand side encodes all the interactions this particular species, right? Because there's an index on here for every species you can think of, whether it's a quark, electron, whatever, a proton, or dark matter. There is some interactions it has that's encoded in what's called the collision term. And that's where all the fun happens. It's a very unwieldy mess. So let's see. So that's what you do. This F, in principle, can have any distribution it wants, right? It can look like, but we know, for the most part, if things are in thermal equilibrium, they follow the Maxwell-Boltzmann distribution, and this F just looks like a Maxwell-Boltzmann or a Bose-Einstein Fermi-Dirac, depending on exactly what limit you're in, distribution. So let me do what I said I wanted to do. I want to learn about the number density of dark matter during this freeze-out process. So what I'll do is I'll integrate this equation over phase space, right? And it turns into something which you're probably used to seeing. Although this right-hand side is probably not something you're used to seeing, but you're used to seeing this expression for how number density evolves with time in an expanding universe. So what is this right-hand side? So this right-hand side is an enormous mess. And since we only have 5 minutes, I'll write it down anyway. So let me, just for the sake of argument, number these species. These numbers may, it may be these are the same particles, but let me just keep track of them. It may just be dark matter annihilating against itself, but let me add indices to all of these to keep track of things. Okay, then you can ask what the right-hand side is, and then I have to be a bit more careful, right? I suppose there's a 1 here as well. This right-hand side becomes integral F1, F2, F3. I'll explain all the signs and things in just a second. It's so hard to write down. Let me write it down first. 1, 2 to 3, 4. So this is the matrix element for the forward direction. Okay. And then I have the matrix element for the backwards direction. 3, 4 to 1, 2. And then there are some delta functions to keep track of momentum conservation. But you're starting to see something that looks vaguely familiar, right? You're starting to see bits and pieces that look like a scattering amplitude calculation. Right, there's matrix elements, there's 2 pi to the 4, there's delta functions, and then I have to integrate over phase, I've already put the integral. I have to integrate over phase space. And by the slash here, I mean that, let me write down one of them just so you know what I mean. 2 pi cubed 2e1, the Lorentz invariant part of phase space. So that's what the slash means. For the others, I've just suppressed the denominator part. Does that, I know you can't see down here, I apologize, I should have thought of that earlier. Can you all see that? Does it all make, is it legible first? It doesn't have to make sense right now, but it has to be legible. Anybody complaining? Don't be shy. Tom's about to complain. So this is an ungodly mess, right? But luckily, there are a whole bunch of approximations we can make that are not unreasonable approximations to simplify this. So, the plus minus. So if the particle I'm talking about is a boson, you pick the plus. If it's not, if it's a fermion, you pick the minus. Okay, and this is Bose enhancement, Pauli blocking, right? When you have these reactions, you have to worry about, is that state already occupied if I'm a fermion? And then that suppresses that reaction. And then the converse thing for a boson is if it's already occupied, I get this Bose enhancement. Okay, so I have to keep track of these pluses and minuses. But secretly, I don't, because I'm now going to make the approximation that the temperature that we're talking about is far less than the energy of the particles, right? And therefore, I'm going to assume everywhere that This is approximately Maxwell-Boltzmann, so it's exponentially small. And so everywhere where I have a 1 plus minus, I can replace that with 1. Okay, and I don't care about the plus minuses. So that's the first approximation I'm going to make to simplify my life. The second approximation I'm going to make is that the right-hand side is standard model particles. So right now I'm thinking about the process dark matter annihilating against itself or being created by standard model particles scattering. But the standard model has a lot more going on, right? It's got photons and it's got electromagnetic processes and all sorts of other things with large cross-sections. So I'm going to assume that the right-hand side, the standard model states, are already in thermal equilibrium, and nothing I can do to them will put them out of thermal equilibrium. Because as soon as I push them out of equilibrium, some of the standard model interactions will get them back into equilibrium. Okay? So I'm going to assume that this is actually the equilibrium distribution. Okay? Sounds reasonable? That's just making the assumption that standard model states have lots of interactions. Okay. And then in the remaining -1 minute, I'll finish. And hopefully this will turn this ungodly mess into an equation you all recognize. Right? I've already said it. Once you start throwing away all these F's and realizing what you're doing is you have a matrix element, a scattering matrix element for 1, 2 to turn into 3, 4, and you have a matrix element for 3, 4 to turn into 1, 2, and you integrate over phase space. That's exactly what you do to calculate a cross-section. So in fact, I've just muddied the waters by writing it in a confusing way, but I can relate that complicated right-hand side to the thermally average cross-section, which is just your normal cross-section integrated against the So this is just, so using this fact, I can define a thermally average cross-section, which is in other words just calculating the scattering cross-section weighted by the distributions of the ingoing or the outgoing particles. Then I can rewrite this horrible mess, or rather I can rewrite the right-hand side with these approximations as the thermally average cross-section times okay, and again, I use the second approximation there that the standard model states are following their equilibrium distribution, right? And then I can use the final fact, which is called detailed balance. Let's just, I'll go this way. At equilibrium, if you're in equilibrium, then the forward reaction and the backward reaction are happening at the same rate. And that tells you that in equilibrium, right, the number densities have to be equal across the two sides of the equation. So then that allows me to turn this into, using that, into N1, N2. Oh, sorry. I'm doing it for N1 right now. But then I'm also going to make the further assumption that, as is the case for most WIMP models, that the dark matter is Majorana in nature and there's no difference between N1 and N2. Right, so now I get to get rid of, so notice what I did is I got rid of the standard model entirely from this expression, right? And now I get to get rid of the indices N1 and N2, and they all just square. So then I have equilibrium squared minus N squared. Okay, and I get rid of this index. And now this is an expression you probably all know. Right, this is the Boltzmann equation for a WIMP, or for a dark matter for that matter, in the early universe, right? In an expanding universe, I beg your pardon. There's a term here to do with the expansion of the universe, and then there's a term here to do with forward and backward reactions. Which part of this expression is winning? Whether going that way or that way is winning. Okay, so I'm over time. So what you should do for tomorrow is solve this equation in all possible cases and get back to me. No, we will solve it like too many times, hand wavy and then in detail and stuff like that, unless Jim beats me to it next time. But this expression is for a dark matter particle in thermal equilibrium with the standard model, right? And then the question we're going to ask ourselves is, let's make that assumption it's in thermal equilibrium and solve this equation. What does it predict for how much dark matter there is out there? And the amazing fact we'll find is that if this cross-section is weak scale, right, you've heard this story before, but if this cross-section is weak scale, you end up with the right number density to explain that pie chart that I started an hour ago with, okay? And that is the origin of the WIMP story of dark matter. And my hope was to get through the freeze-out today and then start on SUSY tomorrow, because that's the canonical explanation of WIMP dark matter, but we'll get to it eventually. Questions? Yes? Can you speak up, sorry?
WIMP dark matter cannot be in the AVP scale.
WIMP dark matter cannot be in the, we'll get to that. So that's called the Li Weinberg Band, and that'll be one of the calculations we'll do when solving this equation tomorrow. Other questions? No more? Then we can all go, oh yes, sorry.
So in this calculation, have we assumed that the dark matter is a fermionic particle? Since you said that it's Majorana.
No, I have not assumed, I shouldn't have said Majorana, I should have said it's its own antiparticle. That's all I assumed, yeah.
Should have said what?
It was its own antiparticle. I don't think I had to assume it was a fermion. I just had to assume that there was no difference between the indices 1 and 2. But in fact, this equation is true whether it's a Dirac or a Majorana fermion. Right? But it's, yes. Yes. I have not mentioned the word R parity, but it was brought in through the back door when I told you that dark matter's lifetime was very, very long. Okay, so we'll get to R parity and stuff tomorrow when we talk about SUSY. But that is one way you can explain the long lifetime of dark matter. Oh, you mean why I have 2 here? Yeah, so there is a parity that I'm assuming, but that is responsible for the stability and also makes the prediction that it has to annihilate in pairs. That's right. Yes? Yeah, I'm saying they're in thermal equilibrium. That's right. So they're not a. Yes, yeah. Oh, I didn't hear your question. Sorry.
I was saying this equation is valid. The assumption of the dark matter is equivalent with the standard model.
That's right.
This equivalence means both thermal and chemical.
So there's chemical and kinetic equilibrium. That's right. And what I've been thinking about here, I guess, is chemical equilibrium in particular. And then there's the issue of when they kinetically disconnect as well. But so far I've just been talking about chemical equilibrium, number densities. Yes, anybody else? No? Tom's saying we should go eat lunch. When do we have to be back here for?
The next lecture is at 2 o'clock.
Okay, 2 o'clock.